And now you have to think maybe a little like engineers or physicists, I don't know, or mathematicians, whatever you prefer. But you want to convince yourself that what you want to do is true. And what do you want to do? I like to forget about these terms. Basically, that's what we want to do. Why would that be true? Well, here is the reason why it's true. This is a number that sort of goes between 1 and -1 with some phase. Mu E naught, however, over h bar is a very small number. Mu E naught, we're saying, compared to the natural scales of the problem, this energy, mu E naught, is much smaller than delta. And delta is the thing that is related to omega naught, in which h bar omega naught is equal to 2 delta. So essentially, mu E naught is very, very slow. It's an energy which is very, very slow compared to h omega naught. Now, being very small, whatever this is, this time derivative is going to be very small. So beta E and beta G are going to be very small time derivatives, going to move slowly. If they move slowly, over the time that this oscillates, this hasn't changed a lot. And therefore, the average of this function over that time is 0, and it doesn't contribute to the differential equation. It's actually a good argument, even if you don't believe it. You can try to convince yourselves, or maybe I'll try better in some way or something, but it is right. I've tried it actually out with computers and with Mathematica and things like that, and it's really absolutely true that if you think of differential equations as integrals, that you integrate what is in the right-hand side, you can see that if this really, the time derivative is controlled by this, that corresponds to a frequency much smaller than omega naught, these ones don't matter. So it's still interesting, and still, well, you know, it's not trivial, but this is a case where we end up ignoring part of the thing. So what do we get then? I beta E dot is equal mu E naught over h bar, beta G. And the second equation, I beta G dot equal mu E naught over h bar beta E. Therefore, if you multiply by another I here and differentiate, I beta double dot of E is equal mu E naught over h bar, the I extra that we borrowed, the dot here. You can use the second equation. So you get mu E naught over h bar squared beta E. Therefore, beta E double dot is equal to minus mu E naught over h bar beta E. And you see you're rotating with a frequency. Put the h bar here and the h bar here with a frequency that is much smaller than omega naught. So this as a frequency this is like omega naught. So indeed, the rate of change of this thing goes with a frequency is much smaller, and it's all right, actually. So we've had that, and then we can write the solution, finally. So what is it? Beta E of t is cosine mu E naught t over h bar. And the probability to be in the E state is the square of that amplitude. So the probability to be in the E state at time t is the square of that. So it's cos squared mu E naught t over h bar. Again, I'm sorry, this beta is here, and the probability to be in the excited state is the square of CE, but the square of CE is the square of beta E. So I just square this. So there you go. We have this, this thing, and we now have an understanding of how this goes. As time goes by, in fact, as mu E naught t over h bar goes by, this starts as a cosine squared, and it then goes like this. And this is the place when this is equal to pi over 2. So what do we need? We need that the place where this happens, that we can call the time t, be such that mu E naught t over h bar be equal to pi over 2 or 3 pi over 2. Or for those values of time, the probability to be excited is 0, and therefore you must be in the ground state. These two probabilities squared added go to 1, so you're either E or G. So if you have 0 probability to be in E, you will be in the state G. So the whole issue is basically at this moment that you must give the right speed, or for a given speed of the molecules, there will be a time that it takes to traverse. That time is related to the steady state value of this energy, of this electric field, by this relation. So you need the right velocity. The molecules have to be at the right temperature, then they'll have a velocity, so that they travel in such a way that is consistent with this. As they do that, each of these particles that goes from E to G gives out one photon, one quantum of the electromagnetic field, and helps build the time-dependent electric field that we started at the beginning. Now, if you, at some point, for some speed of the molecules, you saturate this and you build some electric field, and then you have your cavity operating at the nominal way. And then, of course, you want to use this for something, so you shine, let it go out and shine those microwaves or do something. And if you want to recharge it, you keep adding nitrogen molecules. Now, this was a great discovery, actually. Charles Townes, Gordon, and Zeiger built this ammonia maser in 1953. They got a Nobel Prize. Nobel Prize, Charles Townes got it in 1964. And he emphasized that these masers do the most perfect amplification consistent with the uncertainty principle. This is a coherent state of light that is built here, and it's much better than any vacuum amplifier or anything like that, because the thing that is giving out those photons is a molecule that is uncharged. So it doesn't disturb the electromagnetic field in the cavity as it goes through. Many times you use an electron, for example, to give out some energy, but the electron itself is charged, so it produces additional electromagnetic fields, shot noise, all kinds of noise. This is absolutely quiet device in which this molecule turns from one state to another, smoothly stimulated by the electric field, because if there was no electric field, it would be an energy eigenstate, and then it gives out photon after photon. So the uncertainty is actually, as in this Nobel lecture, which is fun to read, in fact, you remember delta n, delta phi, supposed to be greater than 1/2. Well, for coherent states, as we more or less discussed, this thing is saturated. And what do you have now? You have a coherent state of light. You may remember that the expectation value of n in a coherent state alpha was alpha squared. And you call this the number n of photons. And the uncertainty in n was in fact alpha. So it's square root of n. So for this thing, we have the situation in which we are working with a coherent state that saturates this. So delta n times delta phi is about 1/2. And delta n is square root of the number of photons. So delta phi is about 1/2 square root of the number of photons. And you can imagine a cavity easily can have 10 to the 12 photons, 10 to the 15 photons, something fairly big. And you get an uncertainty in phase. The thing is coherent. All the pieces of that electromagnetic wave, the phases are very coherent up to an incredibly great accuracy. So, so it's a great discovery and the beginning of many things that were done here, in fact, by Professor Kleppner and others in the 60s with other type of lasers and masers and this whole thing.